All right, welcome to chemistry virtual session, first one of the new year. Very light attendance today. I'm guessing some people forgot and are not back into the swing of school, which is fine. We will get there. Warm up. Which lesson are you currently working on? And did you finish your collaboration project? And I know you turned your collaboration project in, Bella. I remember grading yours. Go look at the modules at the very least if you're like, I don't know which assignment I'm working on. In fact, I'm going to see what assignment is due this week. Okay, you finished your project, you're currently not working on anything today, but we'll be starting tomorrow. Great answer. So let's just take a quick glance at the class because we're nearing the end. And it's always good to not only be aware of how many things you have left to do, but how hard or long some of those things will be. Right, the project's out of the way, which really wasn't that hard or long, but did give you some nice points to your grade. Oh, okay, I see, Aiden. You're not working on chemistry. No, it's fine. Good, at least you're working on something. So we're in the last module here, which is called reactions, right? We've done a lot of the what types of reactions are there. Right, we talked about double and single replacement, synthesis, decomposition, combustion. You guys learned about on your own, which honestly is a little bit of an easier one, I think. So there is this lesson called stoichiometry. It is essentially dimensional analysis, and it's what we started off the beginning of the year with. Don't skip this lesson. I'm going to go through that in a second when I go back to the PowerPoint. There's no assignment here. Right? There's a collaboration option. There's an honors quiz, which we're not even doing. But this will be necessary for you to do limiting reactant. It will even help you with percent yield, honestly, although percent yield's a little easier. So the last two things that they save for the end of this class, this semester, limiting reactant is the hardest one. It is hard, which is why we're going to take time to go through two examples today and talk about the steps to solve one of these questions. Then next week will be our final virtual session. We'll continue talking about limiting reactants, and we will also talk about percent yield a little bit. Percent yield is not as complicated. It's more about finding the percentage of something, right? But you do need a lot of the skills that you get in the limiting reactant problems to do it. Then after that, we're done. So next virtual session, we'll also do our DBA. We'll just tack all that in. We'll do a lot. And then you're basically done. Now, the semester ends when? Thank you, Michael, the 31st. Right? So you still have a lot of time in the class. If you're caught up to where you should be, you really only have 2 more lessons, an exam, and the final. So that's like 4 things left. If you're behind, right, you might have a little bit more. But the end is near, right? And I actually set the class up to end a little bit early so that you have time to revise, you have time to redo things, especially these final assignments because they are hard, right? And you may want to redo the quiz or correct it. So we'll talk about that in a moment. All right, so today we're going to identify the steps that you need to solve a limiting reactant problem. By doing that, we're going to review moles, stoichiometry, which is essentially dimensional analysis, although they're technically different, but they're the same thing, and solve 2 limiting reactant problems together. So I already said this, but I'll reiterate again. Make sure you go through the stoichiometry lesson. There's not an assignment, right? But it's necessary to help you do the rest of the class successfully. Also, it'll be a review for the most part, but it's helpful to go through. All right, so what is a limiting reactant, right? Well, really, this sounds like what it is because it's basically derived from the words here. limiting, meaning it's the first thing to run out, and reactant. It's used in the reactant section of a chemical reaction. So it's on the left side. So this is the reactant that would be used up first in a reaction. So if you're thinking about a chemical reaction, right, you know, like let's say we're mixing baking soda and vinegar together. When you mix them together, they're going to react, and then eventually they just stop reacting, right? They bubble, 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 and then it's done. So really what we're going to do here is we're going to determine which one of those reactants was limiting. Did we run out of baking soda first, or did we run out of vinegar first? If I wanted that reaction to continue for 30 minutes, what would I need to do for that to happen? So really what you're going to be doing is determining the quantity of a reactant that you will need to have a reaction keep going, right? Or in other cases, how much product you can get from the reactants that you're starting with. Helpful in real life scenarios here. I want to make a product. Well, you can't just tell me, oh, well, we're just going to mix some stuff together and like it's going to make a product. Okay, how much is it going to make? What if I want this much? What if I want this? Right? So being able to actually control the reaction to an extent. So the excess reactant will be the opposite, right? That would be the reactant or reactants, because there might be more than one, that's not used up. In other words, there's some left over that's just sitting there doing nothing. And then theoretical yield, which is something that you might have seen before, right? But this is the maximum amount of a product that can be produced. So again, it's going to be based on the limiting reactant. Once you run out of that reactant, you're not going to be able to make any more product. So theoretically, how much should we get? Now, why do you guys think it's called theoretical? What does the word theory mean? Or what would it mean if I was saying something is theoretical? Yeah, you're guessing essentially. Yeah, so it's in theory, right? Or if everything goes perfectly, that's how much you'll get. Do you think that you actually get your theoretical yield? No, right? You usually will get close, and that's what the final lesson percent yield is about. How close were you? You said you were going to get 80 grams, you got 79 grams. That's pretty dang close, right? You said you were going to get 80 grams, you got 20 grams. That seems like there's a problem. So essentially it's, if everything goes perfectly in the reaction, that's how much product you should get. Again, it's theoretical because you usually don't actually get that much, because we can't account for all the factors in a reaction, unfortunately. Okay, so steps for solving. There's a lot of them. Personally, I recommend that you screenshot this slide. I will post the PowerPoint after this virtual session, so maybe you can access it there. But these steps are going to be a lifesaver for you, especially if you work well with steps. So steps for solving a limiting reactant problem is the first step, balance the equation. This is pretty much a step that you would need to do in any situation. So we'll go through an example. Don't worry. Second step is going to be identify the given amounts provided in the word problem. These are word problems, as well as what you were being asked to solve for. So step 2 is literally break down the question. What do you know? What are they asking for? You know, what do you need to be doing here? The third one seems kind of funny because you think, well, aren't we doing limiting reactant problems? Well, we are, right? But really then you have to determine, is this actually a limiting reactant problem? If the word problem provides a given amount for more than one reactant, you know it is a limiting reactant problem. This means you will set up and solve more than one stoichiometry calculation, right? Essentially, this is to get you away from the idea that every word problem results in limiting reactant. Not going to be the case. They could be asking you to predict products of an equation, right? They could be asking you to tell them how many moles of something you would get. Many of the other things we've done throughout the semester could be possibilities. So just because you see a word problem doesn't necessarily mean that it is limiting reactant. However, pretty much the rest of the ones you see will be. Step 4, set up a stoichiometry calculation for each given amount of reactant. And really what you're doing there is you're solving to see which one will be limiting, which again, we'll do an example of. So the lower answer that you get in the end is going to be your theoretical yield, the amount of product you can produce. And again, you're going with the lower one because that means that reactant is the limiting reactant. It's the one that's going to run out first. That's the max amount of product you're going to get. If you go with your highest theoretical yield, you're never even going to get close to that, right? Because you're not taking into account your reactants. So really what we're going to do is, let's say we have two reactants, A and B. We're going to say, okay, if I have this much of A, how much product do I get? If I have this much of B, how much product do I get? Oh, I got less product with B. That means B is my limiting reactant. B is the one that runs out first. Less product will be produced, but that's what's going to happen. Okay. So let's dive into a lovely, lovely example. So this is what the word problem part will look like. If 3 moles of hydrofluoric acid react with 4.5 moles of silicon oxide, how many moles of silicon fluoride can be formed? Okay, so what was our first step? I know I gave you a million things, so you're like, I don't remember. Balance the equation. Okay, so step 1, balance the equation. What will our balanced equation look like? Well, let's see. By the way, I'm going to talk through this entire one. You're welcome to be doing it by yourself. The second one, you're going to get to do a little bit more by yourself. So I'm going to start by looking at my fluorines personally, because I already notice, sorry, I'm trying to get my annotation thing to show up and it's not showing up. There it is. Okay, so text box. Fluorines. I see 4 fluorines on my right-hand side of my equation, and I only see 1 on my left-hand side. So I'm going to start by putting a 4 in front of my hydrofluoric acid. Okay. I see 1 silicon on each side, so that seems good. I see 2 oxygens here on the left, but I only see 1 oxygen on the right. I also need 4 hydrogens, so this is going to work out beautifully. I'm going to place a 2 right in front of my water, and then I'll do a final check here. 1 silicon on each side, 2 oxygens, 2 oxygens, 4 hydrogens, 4 hydrogens, 4 fluorines, 4 fluorines. Looks good. Okay, so now my equation is balanced. Now, the balancing part of the equation is incredibly important. Does anyone want to take a guess as to why it matters that we balance? Because if you skip this step, you're going to get it completely wrong. Like, what are those coefficients that we're writing in a balanced equation? What do they actually mean or represent? And you may be thinking, I have no idea, right? You just said step 1, balance. That's what I was going to do. The number of atoms, yes. It's also going to tell you the amount of moles, right? What this means is that for this reaction to happen, you need 4 moles of hydrofluoric acid and 1 mole of silicon oxide, right? You need 4 quantities of your acid, in this case in a powder form, for this to work, right? Otherwise, it's not going to work. So balancing is key. And honestly, sometimes it's the hardest part. You guys may have noticed some equations you're like, oh, so easy. Others are like these 3 hours of balancing. No, hopefully it doesn't take you that long. Okay, so we have our balanced equation. Moving on to step 2. What do we know? And what are we looking for? I personally like to write these things down, especially if I'm solving one of these questions, because I want to make sure that I'm solving for the correct thing, right? There's 1,000 things you could solve for here. In this case, what do we know? Well, we know that we have 3 moles of hydrofluoric acid, or hydrogen fluoride is what I'm going to guess it is because it's not aqueous, but whatever. 4.5 moles of silicon oxide. So we look at those things and we go, okay. Then we want to know, what are we looking for? Well, we're looking for the theoretical yield of our product, right, of the silicon fluoride. Again, I would refer back to my equation, make sure, yep, that is a product indeed, right? We want to know how much of that can we produce. So, is this a limiting reactant problem? Let's hope, since it's in a limiting reactant virtual session, but heaven forbid, we should check, right? Yes, we're given info for both reactants, right? They told us how much we have of each reactant, and we're looking for a product. So great. That means we're going to be determining which reactant is the limiting reactant and how much product can we produce. So step 4, this is the stoichiometry section, which again, to some of you, if you haven't looked at that lesson, may be sounding like, what the heck is that? It's dimensional analysis, right? So we start off by looking at our balanced equation, which I just copy pasted nice and beautifully here. Hopefully you wrote it down, right? You can look at it on your own paper. We start with both of our reactants and we set up 2 separate dimensional analysis boxes. Now you guys know I like to use the tables, right? You could do it with parentheses, or you could just write them out as on a piece of paper, right? That's fine. I like to do the boxes because it's the easiest way to do it on the computer that I've found. So what exactly did I do? Well, I started with what I know. They told us we have 3 moles of HF and that we have 4.5 moles of the silicon dioxide. So we have our 2 reactants here. This is where the balancing part comes in. Now we look at the moles that we need of each. So all I'm doing is trying to cross off moles of HF. Well, I know that for every 4 moles of HF, that comes straight from my coefficient, I'll have 1 mole of SiF4, right? Because I have a 1 here. Remember, I want to know how much of this product can I produce. So I just look at coefficients. If there was a 20 here, then this would become a 20. Right? Then I would be saying, well, for every 4 moles, I could get 20 moles of this. Again, the reason that we have to do this is because we're not given 4 moles. If we were given 4 moles, then the answer would be 1 mole, right? Because we see that in the equation. Very rarely will you be given the amount in the balanced equation. Also, from a chemistry standpoint, it would not make sense. You're not going to want to mix 4 moles of something when you could do it on a smaller scale. So this is a way, it's almost like you're converting into a smaller quantity so you can basically like cut a recipe in half or cut something in a quarter. Okay, so again, what do we know? We know we have 3 moles. That came straight from the question. We know that for every 4 moles of HF, we produce 1 mole of our product, our silicon fluoride. If we multiply this out, right, we do 3 times 1 divided by 4, we get 0.75 moles. Same thing is going to happen for our other reactant, our silicon dioxide. However, for this one, we have 4.5 moles of silicon dioxide. The ratio of silicon dioxide to silicon fluoride is 1 to 1. They both have a coefficient of 1. So this one's kind of easy because I just multiply by 1 and I get 4.5 moles of silicon fluoride. Again, my goal being to cross out my units, just like we did when we converted between moles and atoms, right? That's actually why I have you guys start off the year with that, so that when I introduce it here, it's not like insane. Okay, so based on this, which reactant seems like it's the limiting reactant? Which reactant is going to produce less product? The first one, exactly, right? 0.75 is much less than 4.5. That means that HF, hydrogen fluoride, is our limiting reactant. Okay, so we're not quite done, but we got steps 1 through 4. So now if the question asked you, which one's the limiting reactant? Well, you would be done. You would say HF, end of story. Most of them aren't that simple, right? Then they want you to tell about the product or the yield or whatever. So we go to our final step, which is analyze, right? Again, going back to what is the question asking me? So our limiting reactant is HF because it produces the least amount of product with the amount of moles we were given of it. That means that the max amount that can be made is 0.75 moles. Now, this could involve you having to further translate this. You know what they might ask you to get? Grams. Because again, if you're in a lab, you're going to measure grams to be able to mix things together. So you can convert from moles to grams using your molar mass, which we will review. But this could go further than just moles, right? Keep that in mind. They could even ask you about the number of atoms. You're going to have to recall all of those conversions: moles, atoms, molar mass, grams, etc. Okay, so let's try another example. Here's my, my steps condensed into less words, by the way, which might be something you want to write down as well. But let's check out what this question says. If 35 grams of carbon reacts with 58.5 grams of oxygen gas, how many grams of carbon dioxide can be produced? And then they provide our equation. Again, they might not even provide the equation, and you might have to write it and predict it, right? That would be a way to pull in everything that you've learned. So let's start by balancing. I'm going to give you guys a few moments here to determine if we even need to do anything to this equation or if it's balanced. Also, I recommend that you write this down as we go through this in the steps. All right, so what do you guys think? Do we need to balance this equation? No, right? It's already balanced. Nice and easy for us. We have one carbon, we have one carbon, we have two oxygens, we have two oxygens. Here's a bonus. Which kind of equation is, or which kind of reaction is this? Is this single replacement, double replacement, decomposition, synthesis, or combustion? It is synthesis. You were right, Bella. Right, so this is a synthesis equation. We're taking two things, we're combining them together, we're getting a new thing. Okay, so let's do our steps. We balanced? It's balanced. That's nice. Everything has a coefficient of 1. Great. What do we know, and what are we solving for? Okay, well, what do we know? We know that we have 35 grams of carbon. We have 58.5 grams of oxygen. And we want to know how many grams of CO2 can we get. Okay, first thing I'm noticing is that we're in grams now, not moles. So that's going to add another step here, right? But it's the same concept. Okay, so we're looking for carbon dioxide, which is in fact a product. We come to our third step here. Is this a limiting reactant question? Yes. Again, why? Because we're given both of the reactants, we're solving for a product. We want to know how much is made. All right, stoichiometry. Here is an example of what we would do with carbon. Okay, we have 35 grams of carbon. Next step, since we're in grams, is going to be molar mass conversions. We need to get to moles. Why? Because our coefficients in our equation are moles. We can't really do anything with grams. We need to be in moles. So, first step is look at the periodic table, which conveniently I have one right next to me, and find the molar mass of carbon, which remember, molar mass is just that atomic mass number. Atomic mass equals molar mass For carbon, it's just carbon by itself, right? So that's pretty easy. Carbon is 12.01 as its atomic mass. That becomes its molar mass in grams per mole. If we were doing carbon dioxide or oxygen or other things that have more than one, right, we would maybe have to do a little bit of addition here. Okay, so we have that set up. We have our 12 grams of carbon per 1 mole of carbon. Well, guess what that's going to help us do? We're now able to get rid of grams. And we're in moles. That's great. Now, remember what we're doing here. We're looking at products. We're back to sort of where we started in the first question. If we have 1 mole of carbon, how many moles of carbon dioxide will that produce? 1. Again, all we do is look at the equation and look at our coefficients. So when we have 1 mole of carbon, because we don't have any coefficient here, we also have 1 mole of carbon dioxide, right? 1 is always implied, guys. If you don't see a number there, it's 1. Just like in math, if you see x, right, that's the same thing as 1x. However, you don't write the 1, you just leave it off. It's the same thing here. You don't write the 1 in front of it, but it's still there. So now we've converted from moles of carbon into moles of carbon dioxide. That's great. Now we need to get to grams though, right? Because why? Because they're asking us for how many grams could be produced. So for carbon dioxide, to find our molar mass, again, we look at the periodic table, and we're going to need 1 carbon and 2 oxygens. So carbon is 12.01. Oxygen's mass is 15.999, and we're going to have to add 2 oxygens. So we end up getting 44.01 grams per mole for carbon dioxide. So now our moles of carbon dioxide can be crossed out, and we're left in grams. Okay, we then have to do our math, right? Which in this case, we would do 35 times 44.01 divided by 12.01, which will give us a lovely final answer of 128 grams of carbon dioxide. Okay, seems pretty good considering that we only started out with 35 grams of carbon, but from just 35 grams of carbon, we would be able to produce 128 grams of carbon dioxide. Seems pretty good. However, are we done? We have 2 reactants, right? And we only looked at 1. We now need to figure out how much carbon dioxide will oxygen produce. So we need to do the same exact thing, except with oxygen. So type a 1 in the chat if you would like to try to do oxygen by yourself using the same exact setup, except you're going to be using 58.5 grams of oxygen. Or type a 2 in the chat if you'd like for me to go through setting it up. I mean, obviously I'm going to go through it at the end, but would you basically type a 1 if you'd like some time to try to do it by yourself first? Okay, we got some 2s. Okay, so if you do want to try it by yourself, Bella, you might want to maybe just mute me for a second or just lower your volume, right? And you can kind of try to set it up by yourself, and I'm just going to be talking about it. Okay, so biggest problem, of course, being that I don't have enough space here. I'm trying to remember if I made my next slide blank. No, I didn't. Okay, so let's think about how we would set this up. Get some space here. Okay, we're going to start by writing out how much oxygen we have. We have 58.5 grams of oxygen, of ox. Okay, that's our first one. Our next step is going to be to get to moles, right? We can't do anything with grams. We need moles so that we can use the equation. So we need to find out what our molar mass of oxygen would be. Well, we just found out that it's 15.999 for 1 atom of oxygen. Well, we have 2. right? Because oxygen binds together and is diatomic. So we're going to have 15.999 plus 15.999, which results in our atomic mass being 31.998 grams of oxygen per 1 mole. Okay, again, super helpful because now we can cross off grams of oxygen and we're in moles of oxygen. So we're off to a good start. Now we go to the equation. We know that for every 1 mole of oxygen, we produce 1 mole of carbon dioxide. Again, this one's kind of easy just because they all have ones in front of them. That does not usually happen, by the way. But it's kind of nice here. So for every 1 mole of oxygen, we produce 1 mole of carbon dioxide. Cool. Are we done? No, right? Because now we need to go back to grams. Because again, we're being asked how many grams of carbon dioxide would be produced. So the next step here is going to be to find our molar mass of carbon dioxide. So we know, well, actually, we already did it because we did it for the last question. So why not use our same thing right there? We know that 44.01 wait a second, do I do this backwards? No. 58 grams per mole, mole. Okay, no, I didn't. Whew, I was like, did I do this wrong? Whew, that's what happens when you do limiting reaction questions, though, is that you get almost to the end and you're like, did I do this right? You probably did, right? But just check. 1 mole CO2. We want to know how many grams are in 1 mole of CO2. Well, we could add them up, right? Carbon is 12.01. Oxygen is 15.999. If we do that, we get 44.01, which we already knew from before. And now our moles of CO2 will cross out and we'll be left with grams. And again, now we do our little multiplication division. So we do 58.5 times 44.01, which is like 2,000 something. And then we divide that by 31.998. And we get 80.46 grams. Okay. Oh, not of O2, sorry, of CO2. Okay, so with the oxygen that we have, we can only produce 80.46 grams of carbon dioxide. Whereas with the carbon we have, we can produce 128. So which one will be our limiting reactant, excuse me, the carbon or the oxygen? Great, Michael, the oxygen, right? Oxygen will produce less product. That means that it is your limiting reactant. That means the most we could produce, theoretically, again, is 80.46 grams of carbon dioxide. The only way we could change that is if we added more oxygen, right? Or we took away carbon to the point where carbon became the limiting reactant. So this is a good thing to know. Actually, I want to wait for Bella to be back. Okay, good. So you can hear this too. The limiting reactant is not set in stone. It will always depend on the values that you're given, right? So if we changed this to be 14 grams of carbon, for example, let's say that instead of 35, we change this to be, let's do 15 instead. to 15 grams of carbon. Well, that's going to change all of our math, right? In fact, let's see what you get if you only had 15 grams of carbon. 15 times 44.01 divided by 12, right? If we only had 15 grams of carbon, we would only be able to produce 55 grams of carbon dioxide. And then guess what? Carbon would then be our limiting reactant, right? So it can change. So if you're solving one of these and you think, okay, oxygen's the limiting reactant, that does not mean that it will be if the numbers change. So be aware of that, right? This is completely dependent on the quantities that you are given in the question. The limiting reactant is subject to change depending on how much products or how much reactants you put in. Okay, so again, our final step here is to make sure that we've actually answered the question. Let me erase all my drawings here. I believe on the next slide I had a nicer written out version of the oxygen. Yeah, 80.05 of carbon dioxide can be produced, right? So we just discussed this, that our limiting reactant will then have to be oxygen, right? And how much CO2 can be produced? 80.05 grams. And that will be the answer to our question, right? Again, refer back to the question to make sure you're answering what they're asking. Are they asking you just which one's the limiting reactant? Are they asking you about how much product can be produced? Also keep in mind from our first question, oops, Zoom is giving me a lot of issues right now, that we may have two products. So make sure that you're solving for the correct one. This question would be a lot different, for example, if we were asked about water instead of about the silicon fluoride. So make sure that you're reading what the question asks you, because there could be multiple products. Now, for it to be limiting reactant, they have to give you information about the reactants. Okay, so that's going to be it for today. That should give you guys enough of a head start to be able to attempt this limiting reactant lesson and quiz. Again, refer to the steps, right? Either the long ones that are explained here or the short version of the steps that I have here, right? Balance, what are we solving for? Is this actually a limiting reactant? Stoichiometry, analyze. And that way, if you follow those steps, right, then you're going to be good to go. So I will post this PowerPoint. I am going to give you guys a code word in the chat right now that you can use for 5 bonus points on this limiting reactant quiz, because it's a little challenging, right? And again, chemistry is a process like math that builds and builds and builds. So this is sort of the culmination of all the stuff we've been doing all semester. So if one of these areas feels really hard to you, for example, balancing might be the hardest part for you, right? We'll go back and practice that. Maybe doing the dimensional analysis is the hardest part for you. Go back and review those lessons involving that, or look at the stoichiometry lesson. But yeah, I'm going to post this PowerPoint so you guys can use it as a reference, right, with all the examples set up here. And then otherwise, next week, we're going to do another limiting reactant question together. We're going to do percent yield, which we'll just do probably one example, maybe 2. And then we're going to do our DBA. Okay, and next week was going to be our final virtual session for the class. Yeah, so pretty much that's it. Make sure you wrote down the word that you can use for your bonus points. Do you guys have any questions on what we did so far? I see this was helpful. That will help. Yeah, right? So imagine if I had just let you guys do this lesson without me. I remember the first time I learned this, I was like, what? You have to do what? Because it's everything all at once. Okay, so use the code word to get your 5 bonus points. Yeah, it's hard, right? And I don't want you guys to open the lesson and then just go, okay, not doing that. Because you can do it, right? You have all the skills to do these things, and now you have 2 great examples of 2 different situations to use to help you. Also, I recorded this so you can watch this again, right? So if you were like, wait, I want to hear her talk about it again, you can. All right, so recording probably won't be uploaded until tomorrow morning. Otherwise, I'm going to do the PowerPoint right now, and I will then see you guys next week for our final session.